Welcome to Comic Book Physics 101. I'm your instructor, Dan Claes, professor of physics and astronomy at the University of Nebraska, Lincoln. Previously, when we looked into Einstein's theory of relativity in order to explore time travel, we recognized that no form of mass or energy can travel through space faster than light. Today, we'll revisit those ideas as we challenge that conclusion in a lesson on faster than light. 45 years ago, Voyager 1 launched. It left our solar system at a speed of 38,600 miles per hour and is now 14.6 billion miles from Earth. Voyager is not pointed to the Alpha Centauri star system, home to our closest star, Proxima Centauri. Alpha Centauri A is on the left, Alpha Centauri B to its right, and Proxima Centauri is approximately here. At 4.2 light years away, it's a nearly 25 trillion mile trip. Voyager has gone a mere fraction of that distance, 1/2,265. That's just 0.04% of that distance. Given its speed, a trip to Proxima Centauri would take over 8,250 years. And on its actual course, it'll be over 700 centuries until it even passes the star closest to its path. That's no way to promote space tourism. This is the way we want to travel.
Don't strap yourselves in. I'm going to make a jump to Lightspeed.
Or this.
Warp drive, Mr. Scott.
Warp 1, engage.
Comic books are replete with super beings that fly or run at or exceed the speed of light. And faster than light technologies, FTL, have been exploited across the galaxy by Krypton, Thanagar, and Earth's Justice League, the Skrull Empire, the Kree, and the Shi'ar. Is FTL flight really possible? And how might it be accomplished? Just over 2.5 years ago, did you catch this story? A British Airways Boeing 747 set a transatlantic flight record, reaching a supersonic speed of 825 miles per hour. Actually, it never exceeded its normal cruising airspeed of 561 miles per hour, but the air itself, the jet stream it was riding, was clocked at 260 miles per hour. This offers a nice analogy for the warp drive that we'll be talking about today. Now, Einstein argued over a century ago that mass warps space, compressing and elongating it, and gravity is the result of that distortion. Objects traveling through curved space are forced into the trajectories followed by anything falling freely near a large, massive object. How much three-dimensional space is warped depends on how massive an object is. And space is distorted everywhere there's substantial mass. Moons, planets, stars, those bends and curves in space. Those bends and curves in space-time are described by Einstein's field equation. And the indices mu and nu, ranging from 1 through 4, the 4 dimensions of space-time, this is really a set of 10 different equations: coupled, nonlinear, partial differential, tensor equations. And I assure you, each of those adjectives sends a shudder through even the most steadfast physics graduate student. The Riemann-Christoffel tensor R details how space curves in response to the distribution of mass and energy that's specified in an energy momentum tensor T. The tensors are 4x4 matrices, and the Riemann-Christoffel terms expanded out look like gobbledygook. Let's not even pretend to solve these equations, but let me give you some idea of what they do. Notice buried in the expression of each element of R are elements of another tensor, G, what Einstein called the metric tensor. If you've studied electrodynamics, you'll recognize these two Maxwell equations. Gauss's law describes how electric fields bend as they fill in the free space outside any distribution of electric charge. Faraday's law describes how field lines converge on the source of charges that create the field. Differential equations tell us how things curve. What are the little g's in that metric tensor? What do they represent? And what would it mean for them to bend? This differential statement gives the shortest distance s between 2 points, what you think of as a straight line, but here through 4 dimensions. G provides the coefficients that direct the shortest line's trajectory through space-time. When we're working in just 2 or 3 dimensions, this interval just measures ordinary distance. In Euclidean space, or flat space, governed by the rules of ordinary geometry, any short distance s is defined by the incremental components along x and y that contribute to it. And you'll see in this case, all fixed by the Pythagorean theorem. In these cases of simple Euclidean space, the metric tensors take a simple form of 1s down the diagonal and 0s everywhere else. But space need not always be Euclidean. If you traveled from central Arizona straight north exactly 300 miles, then traveled due east for 400 miles, you'd expect to be, quick calculation here, 500 miles from where you started. But if you set your bearings in that direction, a 500-mile leg would overshoot your starting point by something like 1,600 feet. At our scale, Earth's curvature is not obvious, but working with the best surveyor's tools, aligning yourself carefully with the local compass and zenith directions, you'd discover, across large geographic distances, the Pythagorean theorem does not work. We are on a globe. Separation should be calculated with trig. The difference from a Euclidean assumption of 1s running down the diagonal of the metric tensor are corrected by a sine of the latitudinal angle squared. The shortest distance intervals measured across curved surfaces defy the Pythagorean theorem, or perhaps we should say follow their own variation of that rule. The metric tensors describing different curved spaces will all be uniquely different. And just like topography of physical surfaces, need not display the same slopes at every point. The distribution of mass through space-time can give it an irregular topography. It's the metric tensor that describes this topography. The expansion of the universe means the metric tensor must also include a time-dependent factor, that alpha of t, growing all of its entries with time. Those values balloon out, describing the expansion taking place at every point everywhere in space. Even matter not moving much or at all through space still grows further apart from distant points. Each speck, representing a galaxy on this balloon, remains at a fixed point on the balloon surface, yet those specks move further apart from one another due to the stretching of the balloon and the space between them. Galaxies receding from you move together with their neighbors in a local cluster. They don't move with respect to one another much, if at all, effectively stationary in space. And yet, the furthest galaxies, because of the expansion of the intervening space between them and you, are racing away the fastest. Galaxies over 13 billion light years away are receding from us at speeds greater than the speed of light. They're not traveling through space that fast, but the space between us is expanding that fast. Almost 30 years ago, newly minted PhD in astrophysics from the University of Wales and admitted Star Trek fanatic Miguel Alcubierre, now a professor at the National Autonomous University of Mexico, found a solution to the field equations that formed an interesting distortion that rippled wave-like through space-time. While the special and general theories of relativity have an absolute injunction against matter traveling through space faster than light, there's no known speed limit on space itself, as we just saw on the previous slide. Here's a representation of an otherwise flat region of three-dimensional space, warped about a spaceship. The warping of space-time is pretty hard to depict, so you'll just have to imagine that the three-dimensional space it all occupies has been collapsed into that grid shown on the floor. What are those distortions dipping down in front of the spacecraft and rising behind it supposed to be describing to us? there's an undistorted pocket in space-time where the spacecraft sits. The distortions that define the rocket's edges move together like a wave rippling out in advance and behind the ship, traveling with unbounded speed. The ship need only crawl across the space within the bubble at subliminal speeds, carried by the wave in space-time, like the British Airways ship rode the jet stream. Think of the ripples crossing space-time as bunched up in kinks in an endlessly long rug that runs the length of an infinite corridor. This is actually a dish towel I lay on my dining table. As the wave moves from left to right, more of the rug is pulled in and bunched up in front, while the bunching relaxes behind, restoring flatness. If you just stepped over the kinks, you'd cover much more ground than you would have in a step through normal flat space. Now, no human should be crossing through regions of such extreme distortion, so let's place our passenger within the Alcubierre region, where the ship rides within the eye of a storm, a bubble of flat space-time, safe from the tidal forces of the warped regions. The ship is carried like a surfer riding a wave. But what distribution of mass or energy could create this moving warp bubble? One thing's clear: whatever is happening in front of the ship, the reverse happens behind it. Something elongates the space behind the ship, and something else contracts the space before it. The math suggests that regions of positive mass or energy must be concentrated before the ship, and regions of negative mass or energy, whatever that might be, behind. Early calculations suggested enormous quantities of each. The initial estimates called for an amount of this exotic negative matter greater than the mass of the entire observable universe. That aside, just what is negative mass? Negative mass is not antimatter. We know because we've created antimatter. For example, antiprotons in 1955 at the Berkeley Bepitrons. When a high-energy proton collides with a stationary momentum equals zero target proton with sufficient energy, antiprotons can be generated through E equals mc squared by the energy of the impact. Antiprotons are not created singly, you'll note, but paired with an extra proton. The energy must create both the ordinary proton and an antiproton in the same process, taking into account both the mass and momentum of each particle. Assuming the antiproton has the same mass as the proton, the minimum energy required can be predicted and found to be exactly equal to the rest mass energy of 7 protons. In the 1955 experiment, a beam of protons was focused on a carbon target. Magnets swept in just negative particles of precisely the momentum they expected the proton and antiproton pair to leave the collision, and Cherenkov detectors at the end of the line distinguished particles with speeds between 75 and 79% the speed of light, bounding the calculated speed of the expected antiprotons. Additional steering and detector elements allowed them to separate antiprotons from contamination by any stray pions or kaons that might have been swept into the arms of the detector. They controlled the energy of the original proton beam and found no antiprotons until the beam approached 6 GeV of energy. The spread in the turn-on curve is due to the internal energy of the vibrating atoms in the carbon target. The curve remained flat above that. The perfect match to the predicted energy demonstrated that it takes positive energy to make both the matter and antimatter. An antiproton is not negative mass. It is mass. As far as we know, there's also no such thing as negative energy. If there were, the vacuum of space would be unstable against the spontaneous creation of positive and negative mass pairs in infinite number with continuous ongoing annihilations. The vacuum of space would be chaotic, something we don't observe. And as far as we know, there's no such thing as negative mass. Here's why. Newton's second law gives the acceleration that a force produces on the mass it acts on. What would his theory of gravity predict were negative mass to exist? Positive mass times positive mass would generate a positive gravitational force of attraction. Choice A. Negative mass times negative mass, negative times negative is positive, also a positive force of gravitation, attraction. Selections A and D answer this question. In the case of a pair of equal-sized but oppositely signed masses, positive and negative mass, the force would be negative, the opposite of what happens for positive mass objects. Oppositely signed masses would gravitationally repel one another, not attract. It gets weirder than that. Using Newton's second law, we see the common gravitational force acting between these objects repels the positive mass, which attracts the negative. We'd have a pair of accelerating objects, the negative mass chasing the positive matter that it's attracted to, and the positive matter racing away. And together, with ever-increasing speed, which would completely violate the conservation of energy. We've never seen any such behavior anywhere, anytime. If there's no such thing as negative energy and no such thing as negative mass, can an Alcubierre warp drive ever be built? Just 2.5 years ago, recent astrophysics PhD Eric Lentz, with pandemic-provided idle time, revisited the Alcubierre calculations, claiming to find a new solution with only positive mass and energy distributions. What was important was relative densities, areas with a lower energy density than adjacent regions, with neither of them necessarily negative. Promising. A few months later, published in the same journal, Lavinia Heisenberg and master student Sean Fell found a number of classes of solutions of warp drives, some requiring as little as 1/10 the mass equivalent of the planet Jupiter, and positive mass at that. These claims are controversial, as Alcubierre's had been from the start. And then this past spring, a deep dive analysis of all three papers led to a detailed proof of a theorem these authors argued all such warp drives must satisfy. Their null energy condition requires that the integral of the sum over the energy densities across the entire volume of the warped region must sum to zero. And the pictures of the Alcubierre warp bubble suggested that had to be true. Now, in the months since, there have been considerable discussion between Lentz and the Santiago Visser group, trying to clarify and explain one another's work, which at the moment remains unresolved. I find it exciting just to think that the subject of warp drives inspires theorists to look into it seriously. If negative energy densities, though, are required, as the null energy condition seems to suggest, is this a death knell to the whole notion of warp drives? What gives we physicists pause is that 27% of the universe appears to be made out of dark matter, something we do not understand, and 68% seems to be made out of dark energy, which is driving the current expansion of the universe. Dark energy has that anti-gravity characteristic of the exotic matter demanded by the Alcubierre drive. Bam. But of course, we don't know what dark energy is, if it's even stuff that we might be able to harvest. And if it is, how do we collect it? How do we store it? How do we manipulate it? How do we fashion it into the energy distribution that would create the space-time distortion like the Alcubierre envisioned? Until another breakthrough is reported. For now, I'll just have to say, to be continued.